Hi there! Welcome to the 7th episode of the filters tutorial. It is finally time to talk about active filters, and we will do so by introducing the subject first, and then go through a couple of simple examples, the active low-pass filter and the active high-pass filter. And as it has become tradition, each example would be followed immediately by a demo in the lab to see how they work in reality. Without any further ado, let's begin. Hi there! I am Carlo Carrano, and this is Electronics Engineering Made Easy. To talk about active filters, we need to begin with the concept of amplifier with negative feedback. Such an amplifier is made of a module with gain G, which provides directly the output based on its input. The input of the amplifier is given by the difference of the signal coming into the device minus the output of the device itself, adjusted by a certain factor f. The path that goes from the output of the device back to its input through the block F is called negative feedback. G is the amplification factor of the amplifier. F is the feedback function, otherwise known as the transfer function of the block with the same name. We can go now through a simple calculation to figure out the transfer function of the whole system, made of the two blocks and the other in front of the block G. Let's freeze the image for a moment and let's analyze what we are seeing. The input of block F is the signal VO. The output of block F is its input signal multiplied by the transfer function, and so it is F times VO. The output of the other, considering the negative sign, is therefore VI minus FVO. And this is basically the signal applied to the input of block G. As a result, the output VO of block G is given by the product of the input signal and the transfer function f, like this. And now we can rearrange this equation, putting it into this second form. We can then adjust it like this. And finally, we can write the transfer function of the whole system as the ratio between VO and VI, which can be readjusted one more time, dividing both numerator and denominator by G. Now, if we use an amplifier that has a very large value of amplification, we end up with the ratio 1 over G almost equal to 0, and so we can write the transfer function in its final form with this approximation. Look at it carefully. The transfer function of the whole device is the inverse of the transfer function of the negative feedback only, nothing else. Why do we need this? Because this is the basic notion of how the active filters work. We can obtain an active filter by using an appropriate passive filter in the negative feedback of an amplifier. So how do we do this in practice? Since we need an amplifier and a component that performs the difference of two signals, the first thing that comes to mind is to use an op-amp. We can use the huge amplification of the op-amp along with its capability of subtracting two signals using the inverting input. Here is a possible implementation with a generic op-amp. We extract VO from its output, and we insert VI into the inverting input using an impedance Z1. And then we complete the circuit with an impedance Z2 connected between the inverting input and the output. We also leave alone the non-inverting input by connecting it to the ground. So what do we have at this point? We have an amplifier with a negative feedback, and we have a feedback function given by the ratio between Z1 and Z2 with a negative sign. And in fact, we know already from the op-amp theory that the transfer function of a circuit like this is H equals negative Z2 over Z1, which is exactly the same as the inverse of F. At this point, we can change the behavior of the amplifier just by changing Z1 and Z2, which can be made of any combination of resistors, capacitors, and inductors. Let's see how this works in practice, making an example. And for that we use a resistor for Z1 and the parallel of a resistor and a capacitor for Z2. So Z1 is equal to R1 and Z2 equals to the parallel of R2 and C, which we can write as the product of the resistance and the capacitive reactance divided by their sum, like this, if we recall how capacitors can be described in the frequency domain. The transfer function H, which is the negative ratio of Z2 and Z1, can therefore be written this way. And this can be readjusted in a few steps, like this. Do you see any resemblance with something we saw when working on the passive filters? Well, this is in fact the transfer function of a low-pass filter, but with an extra factor, the ratio between R2 and R1. And so, this circuit behaves like a low-pass filter, but it is also capable of amplifying the input signal, and the amplification value depends on the values of the resistors R1 and R2. And because of what we have already seen with passive filters, we now know that the cutoff angular frequency is given by 1 over R2 times C, and the transfer function can be finally written like this. And so, observing this function, we see that this function has one pole, omega 0, and no zeros, because the numerator is a constant. And we can also draw the body diagrams for the magnitude and the phase. For the magnitude, we need to start with the logarithmic value of the ratio of R2 and R1 multiplied by 20, which is the amplification in dB of the filter in the region below the cutoff frequency. After the cutoff frequency, because of the presence of the pole, the amplification declines at a pace of 20 dB per decade, or 6 dB per octave. For the phase diagram, we proceed exactly like in the case of the passive filters, since we don't care about magnitudes, and so we only need to consider the pole omega 0, its value divided by 10, and its value multiplied by 10. Then, based on those terms, we can draw the diagram starting with a phase shift of 0, and then the shift becomes negative and drops to minus 90 degrees within the interval centered around omega 0, and then it remains at minus 90 degrees for any value of frequency higher than that. Let's now go to the lab and verify all this theory with a practical circuit. Here is a circuit mounted on a breadboard. This is a UA741 IC that contains one op-amp inside. And these are the two resistors that are part of the negative feedback. This one is R1, in series with the input signal, which I have chosen to be 100K. This other one is R2, also 100K, which is in parallel with a capacitor C of 1 nanofarad. Both R2 and C are connected between the output of the op-amp and its inverting input. These two capacitors are there to filter out the noise from the supply voltage that powers the IC, and they have the usual value of 100 nanofarad that we have seen in several occasions. These two alligators connect the circuit input to a function generator here that is currently providing a sine wave at 100 Hz with an amplitude of 5 volts peak-to-peak. The gray probe is connected instead to the first channel of the oscilloscope, while the second channel is connected to the function generator. This way we can see both the input wave and the output wave. The input wave is the blue one on the bottom, and the output wave is the yellow one on the top. The scale for both channels is set to 2 volts per division, and you can see that both waves right now have a value of about 5 volts peak-to-peak. I have already set up the cursors to identify a delta V of 720 mV, so we can see when the wave reduces its amplitude below the 3 dB that identify the cutoff frequency. So let's now start to increase the frequency and see what happens. Okay, now we are at about 800 Hz, and you can see that the output wave is barely attenuated. Let me adjust the scale a little so we can better see the periods of the sine wave. Okay, now I am increasing again the frequency of the input signal. So you see how increasing the frequency, the output amplitude decreases slowly, at least for now. Let's now increase further the frequency. And here it seems we have reached the point of the cutoff frequency, which seems to be 1.6 kHz. And in fact, if we calculate the cutoff frequency as 1 over 2 pi R2C, we obtain a very close value, sign that we are doing things right. If we now increase further the frequency, the amplitude of the output signal will become smaller and smaller at a faster pace, those of 20 dB per decade we mentioned previously. Decreasing the frequency, of course, will reduce the attenuation and the signal will increase in magnitude. Let's now go back to our drawing board and let's make a second example of active filter. We will use again an op-amp, but this time we will put a capacitor C and a resistor R1 in series with the input signal, and a single resistor R2 between the output and the inverting input. And so this time Z1 is given by the sum of the resistance R1 and the reactance of the capacitor, which is 1 over Sc. Z2 instead is just the resistance R2. The transfer function H of the circuit is again the negative ratio of Z2 and Z1, and we can write this expression. Now we need to modify this expression to make it look like the ratio of two polynomials. And here we can define omega 0 as 1 over R1C, and so we can write the transfer function in steady state in this way, and that can be written as the negative ratio of R2 over R1 multiplied by this expression. In this transfer function we still have one pole, omega 0, but we have also one 0 with the value of 0. Given the 0, the pole, and the amplification, which will be converted in dB, we can now draw the body diagram of the magnitude, and then the body diagram of the phase. And so now we can tell that this circuit is basically a high-pass filter. And once again, now let's go to the lab to verify that this circuit behaves as predicted by the math. Here is the new circuit mounted on the breadboard. I have kept the values of R1 and R2 still to 100K and the capacitor C still to 1 nanofarad, and so the cutoff frequency is still 1.6 kHz. This time, however, we have the inverting input in series with the capacitor C and the resistor R1. And between the output and the inverting input we have instead a simple resistor, which is R2. The non-inverting input is again connected to ground. The function generator at the input of the circuit is now providing a higher frequency, which is currently set to 8 kHz, and we still have the same sine wave as before at 5 volts peak-to-peak. Here are the images of the input and output waves on the oscilloscope. The yellow trace is once again the output. Like in the previous example, both input and output waves have about the same amplitude, and the cursor are already set to identify the delta V of about 0.7 volts. Let's now start reducing the frequency, and we should see the output wave decrease in amplitude. As soon as the amplitude touches the end cursor, we will have the cutoff frequency of this filter. So let's reduce the frequency now. And yes, here we are, and the cutoff frequency is exactly the same as the previous case, which was expected since we used the same value of resistors and capacitors in both examples. And this confirms that we are dealing with a high-pass filter. You can now understand how the theory that we previously studied for passive filters can still be applied to the active filters. Active filters, however, provide a couple of advantages with respect to passive filters. First, we can define an amplification value for the signal, if so desired, to compensate for the attenuation caused in passive filters by the resistors that are in series with the output. And second, since we are using an op-amp to extract the filtered signal, we are actually lowering the output impedance so that we can safely connect any kind of load to the filter without affecting its cutoff frequency. And in fact, we could just cascade two or more of these filters to obtain filter orders greater than the first, without affecting the cutoff frequency, which instead happened in the case of passive filters. There are, however, other ways to obtain second and third order filters that do not necessarily require several cascading op-amps, These are special filter categories, and we will take a look at them in future episodes. And so, to avoid missing the next episodes, don't forget to subscribe and to click on the notification bell. In the meantime, see you in the next video, and as usual, happy experiments!